Welcome everyone. Today we're going to be talking about ionic compounds and the nomenclature associated with them. And so that's going to involve naming and formula writing. So last class we did all of that work for covalent compounds, and now we're going to switch over to ionic. I kind of gave you guys a heads up that ionic is a little bit more involved than covalent, which was the opposite of our bonding unit. And so what we're going to do is we're going to start just reviewing how those ions get their charges. And officially, those charges are related to the oxidation number that is created when they gain or lose an electron. So an oxidation number is the same as the charge number on the electron, so that is the charge on an atom after it has become an ion, so that's when it has gained or lost electrons to become an ion. So again, this should be reviewed from the last couple of units. So we should remember then that neutral atoms always have equal numbers of protons and electrons, so their charges even out, or the word that we've been using is balance out. And so therefore when electrons are gained, that atom has a surplus of those electrons and therefore becomes negatively charged. And on the flip side of that coin, when electrons are lost, that atom has a surplus of protons. Even though the protons don't change, we now have lost electrons, so we have a surplus of protons, and it becomes positively charged. And so remember that only our valence electrons are the ones that are involved in this process. So all of that should be review of where we get these ions, where we get these charges from, and now we're just putting an official name to it. So the oxidation number for the following elements can be found on the periodic table. Remember, we've talked about how each of these elements are in a characteristic group. We called those the A groups. And as a result, everybody in the same group, so the same column, has the same charge number or oxidation number. So for sodium, it's in group 1, so its oxidation number is +1. For magnesium, it's in group 2, so its oxidation number is +2. Aluminum is in group 13 overall, but that's the third A group, so its charge and oxidation number is +3. Silicon is in group 4, and we won't really deal with these guys in terms of ionic bonding as much for silicon and carbon. But from an oxidation standpoint, it does make a +4. Phosphorus, we switch over to, remember the question we asked, is it easier to gain or lose? So once we get past group 4, it becomes easier to gain than lose. Phosphorus is 3 spaces away from 8, so it's going to gain those 3 electrons. In group 5, it is group 6, A group 6, or group 16 overall, where sulfur is, and that's 2 spaces away from 8. Chlorine is in group 7, and that is 1 space away from 8. So again, we're counting up to group 4, and then we're counting down from group 4. Now, argon is a noble gas, so it's not going to make a charge. It's not going to make an ion unless we force it. And so its oxidation state is 0. It's not going to gain or lose because it's already at 8. So where does that apply? This is going to apply in how we write formulas for ionic compounds. When we write formulas for ionic compounds, we're going to write the cation first. Which, remember, is your metal. And we're going to write that symbol including its charge number. And then we're going to write next the anion, which is your nonmetal, including its charge. Okay? Then we're going to combine enough cations with enough anions to create a neutral compound. Now, you don't realize this, but step 3 combined with step 4 using the lowest ratio or the simplest ratio in whole numbers is something you actually already know how to do. So step 3 and step 4 are what we know as the crossover method. And in the crossover method, it says crisscross your charges and reduce if you can. Okay? So the crisscross part makes us a neutral compound because that creates a combination of numbers that equals out our positives and our negatives. And then the reduce part gets at the lowest whole number ratio possible. So again, you already know how to do this. This is also known as, so AKA, balancing charges. So when I tell you to make a formula by balancing charges, what I'm telling you to do is to do your crisscross and reduce. So use your crossover method. So let's look at a couple of these examples. The first one is potassium, which is a +1. Notice that we've started assuming the 1 here and just leaving the sign, kind of like we do with subscripts. We don't include the number 1 when we do subscripts. And chlorine is a -1. So if we take If we take potassium as a +1 and chlorine as a -1, and we crisscross those charges down to make subscripts, my ending formula is going to be 1 potassium and 1 chlorine. Next, if I have calcium, which is a 2+, and bromine, which is a 1-, when I crisscross that, that's going to give me 1 calcium and 2 bromine. Lastly, if I do aluminum and sulfur, aluminum is a 3+, sulfur is a 2-. Again, if we crisscross that down, that's going to give me 2 aluminums and 3 sulfurs. So again, you guys have already done this. You just didn't know that you were actually practicing making the final formulas. So in every single ionic compound, when you make the formula, you are going to be using the crossover method, crisscross and reduce, every single time. Now, one special case that we have, we're going to move down to the next section, so make sure you have your notes. If you need to pause and do that, do it now. One exception that we have with ionic compounds is the presence of transition metals. So that really comes in when we're naming them. Transition metals are just regular metals. They have a charge. But remember that transition metals are special in that they can actually have multiple charges. So for transition metals, I have to have some piece of information that tells me which version of the metal I'm dealing with in order to crisscross it. And that actually comes from the name. So when we name the ionic compounds, we're going to write our cation first. Again, that's your metal. And then we're going to write our anion second. And again, that's your nonmetal. Okay? Your cation, if it is a transition metal, you will also include a Roman numeral in parentheses to indicate its charge. And we'll talk about how we figure that out in just one second. When you name the anion, so the first name is just the first name. The only thing that you might include is a Roman numeral if it is a transition metal. The second name is your nonmetal. And remember last class we talked about the only ending that we ever get to change is to IDE. So that's the only time we're going to use that ending change is on the second name. So on the name of your nonmetal. So I'm going to look at a regular one here. We call this a simple binary. And then I'm going to look at one of these special cases that does contain a transition metal, and we're going to talk about how to figure that out. So, following my rules, I name the metal, and in this case it's sodium, which is just a regular metal, so I don't have to change anything. I'm just going to call it what it is. The second element is sulfur, and so the second name, so my nonmetal name, is going to get the IDE ending. So it's going to become sulfide. And that's it. Notice that there are no prefixes anywhere in sight because we are dealing with ionic now and not covalent. So we left our prefixes with the covalent conversation. Now let's look at this one that contains a transition metal. So if it contains a transition metal, we must crisscross back up. So our crossover method says crisscross and reduce. But I don't know what the charges are here, but I know that the subscripts are generated from the charges. So I'm going to have to work backwards to figure out what the charges were. To do this, we are always going to start with the subscript of the cation. So you always want to check the cation charge, or excuse me, subscript. First. Okay, so how we do that is we're going to look at two different examples. So example 1 is going to be SnCl4, just like what we have up here. I am going to do another example as well. Notice that we have an assumed 1 subscript there. Chlorine, we know, is a 1 minus charge. So the 1 and the 1, they match. As a result, since the 1 and the 1 match, I know that the 4 came from here. So tin has a +4 oxidation state. It's a charge 4. So we would write the name as tin 4 chloride. The second example that I want to show you is PbO2. Now, on PbO2, oxygen's charge is a 2 minus. We know that from the periodic table, but see how that does not match the assumed 1 that's on lead. As a result, I can see that there is a multiplier of 2 from the 1 to the 2. So then therefore there must be a 2 multiplier from the 2 up to the charge of lead. So 2 times 2 is 4. So it would be lead 4 oxide. We're going to practice, and we'll see you back in a bit.